Hello everybody. Today I will discuss the few elements of physics of manufacturing processes. We have discussed so far regarding the electromagnetic analysis and to some extent the heat transfer, fluid flow phenomena, and of course the stress analysis part. But these elements also necessary to understand the mechanism of the or physics of the manufacturing processes. So, maybe not necessarily to discuss in details about all these elemental phenomena that normally happens or may be related to the manufacturing process, but I will try to give some overall view of all these elements, and which is more important when you try to analyze the physical basis of the any kind of manufacturing processes. So, first we will try to look the solid state phase transformation and of course recrystallization, and of course then the melting and solidification. I think few manufacturing process and maybe basis based on the melting and solidification phenomena. And then of course nowadays recent trend to or recent manufacturing technologies, that is called additive manufacturing technologies. So, we will try to give some brief about the additive manufacturing technologies, and of course what are maybe the parameters and modeling approach normally happens in additive manufacturing technologies. Of course, in additive manufacturing technologies we will try to look into both polymeric material as well as the metallic material. Then coupling of the different mechanism. Actually when you try to get some kind of modeling approach, then it involves the several physical phenomena. Sometimes physical phenomena we represent in terms of the governing equation, and sometimes some constitutive relation we normally use to explain all these physical phenomena. So, now if there are several physical phenomena, then what way we can couple to make an efficient algorithm to explain the different mechanism or physical basis relevant to the manufacturing process. So, first I will look into that solid state phase transformation and recrystallization. So, of course, it is more relevant. The solid state phase transformation is recrystallization is one phenomena, and it is related to the solid state phase transformation. So, phase transformation means we simply understand that transformation of the phase one phase to another phase, and of course this transformation of the phase may or may not associated with the change of the composition. For example, if we look into that cubic and tetragonal phase. So, one and like in that way we can say that even in case of iron also there may be change of the phase from FCC iron to BCC iron, that also we can consider two different phases, and of course this transformation is associated with following certain kinetics. That means once there is a phase transformation from one phase to another phase. So, what may be the intermediate stage, how this phase transformation happens, what are the kinetics mechanism are responsible for that to try to look into that aspect. So, definitely we normally use this terminology, the phase transformation kinetics. This phase transformation kinetics either can be diffusional or it can be non-diffusional, and of course what we can explain, there is a mass transport and it is associated with that. So, therefore, diffusional and diffusionless kinetics related to phase transformation, that depends on the more or less it is a time aspect. Basically time phenomena is important here to explain the diffusional and non-diffusional or diffusionless transport. Now, any phase transformation normally happens one phase to another phase. It is associated with some sort of nucleation and the growth processes. So, definitely whether it is solid state phase transformation, that means that phase transformation happens in a solid state, or during the solidification also, that means from liquid phase to transformation to the solid phase. Both the cases it is associated first the formation of the nucleus, and then of course this nucleation formation depends on, so there are so many driving parameters that actually favors to create the nucleation phenomena, but that is a separate chapters. We will try to discuss in the respective module that part. And of course nucleation happens, and then the perspective growth of this nucleus after the formation of the nucleation, and that way it creates the another new form, new phase. So, now of course when you try to analyze the phase transformation, first we need to understand what are the driving forces are required in case of phase transformation, what are the kinetics, that means whether diffusion or diffusionless, or what are the mechanisms of this transformation. So, we can take one example also, even if you look into the heat treatment process, and of course, the heat treatment process, if we know what is the heat treatment process. So, simply we make the sample available. First step is to increase the temperature of a particular temperature and keep it for a long time, hold that time, such that we can allow the respective transformation, and then after that we normally follow the cooling, and of course, this cooling may happen at different rate of the cooling. So, that simply introducing the different medium, cooling medium, we can simply vary the rate of the cooling. For example, it may be furnace cooling, it is a very controlled cooling, it is possible to produce, or it may be simple normal air cooling, or sample can be cooled just keeping in the water quenching, that means within the water. So, all this different medium, so there the rate of the cooling rate are different. So, that depends on the accordingly that microstructure actually develop in a particular sample. So, therefore, it is also one example of the phase transformation, one phase to another phase it forms. Apart from that, if you look into that, phase transformation is mostly associated with the change of the microstructure. So, maybe initial microstructure, after phase transformation the microstructure can be different. But what are the kinetics? Kinetics already discussed, but we can further divide the kinetics of the phase transformation in the other way also. First look into that diffusion dependent with no change in the phase composition or number of the phase present. So, that is one kind of the kinetics, and we can take example that melting and solidification of the pure metal. If you look into that example, melting and solidification of the pure metal, that also happens, transformation of the one phase to another phase, liquid phase to solid phase. But in these cases there is, since there is a pure metal, so there is no change in the composition of the metal, and of course, number of phase present is the same. So, it is a simply liquid phase. Now, after transformation it becomes only the solid phase. But if we take the melting and solidification of the alloy system, then there is a possibility of the even phase liquid phase to solid phase, but within the solid phase there are, it may mixture of the other kind of the phases may present in case of alloy. So, therefore, in that cases the diffusion dependent phase changes in diffusion dependent kinetics, but with changes in the phase composition, or there is a number of phase present. That is simply we can look in the iron carbon equilibrium diagram. Here we can see that there is some eutectic reaction or eutector transformation. If you look into that equation, so it may either form in the from one solid phase to decompose into two different solid phases during the cooling of a particular following certain cooling at a particular temperature. So, that kind of eutectic or eutector transformation is simply example of the, here also diffusion dependent, that means diffusion happens and at the same time there may be change in the phase composition or number of phase also changes. So, that is the kinetics of the phase transformation. So, of course, there is another kinetic, that is the diffusionless phase transformation. Diffusionless phase transformation normally happens if we follow very fast cooling process, and that means less time is given to the system to give sufficient time to diffuse the atoms when there is a transformation of the phase, one phase to another phase. So, therefore, in that cases it may be most of the cases accompanied by some kind of the small displacements and near about the all atoms in a structure. So, it is associated with that. So, one example is the martensitic transformation, that is a diffusionless phase transformation, because martensitic transformation normally happens in case of steel, and then when you try to follow very rapid cooling of a particular sample. Now, of course, what we understand that throughout the phase transformation, apart from the kinetics, normally phase transformation is a needs some finite time, definitely in is a time dependent phenomena. But if we say it is a diffusion dependent, diffusion normally takes a long time, and if it is diffusionless, in that cases the time requirement is very less. So, that is the difference. So, diffusion dependent phase transformation is a relatively slow process, and of course, in the relatively slow process in the sense that it takes a long time to transform one phase to another phase, and final microstructure simply is a function of the rate of the cooling. Definitely in the diffusion dependent phase transformation, the different microstructure we can produce if we follow simply the different cooling rate. But of course, in general diffusion dependent transformation normally takes large time as compared to the diffusionless phase transformation. We can look into that Definitely phase transformation involves change in the structure and composition, and structure and composition is simply the rearrangement of the atoms. We can rearrangement as well as the redistribution of the atoms, and that happens through the diffusion mechanism. So, that is normally associated with the phase transformation. So, of course, already discussed, it is associated any kind of phase transformation, it is associated with the first the nucleation step and then the growth step. So, nucleation is simply formation of the stable small particles or nuclei we can say, and that is of the new phase. And of course, this normally formed at the grain boundaries, and this normally formed in the grain boundaries. Even in case of solid state solid state phase transformation, in that cases the nucleation normally happens. That means we can say the new phase, it is a very small size, actually creates near about the most of the cases near about the grain boundary. And then the growth phase is the of the new phase. So, that means when the new phase forms, the new phase actually grow if we gets the favorable conditions, and of course, this new phase grow favorable conditions, and it actually consume the old grains expense of the original phase. So, therefore, nucleation as the growth is associated with the any kind of the phase transformation effect. So, graphically if we look into this transformation kinetics, or maybe what we can say that the typical transformation curve, we can see that it is a fraction of the transformation. So, that means fraction of the transformation may be it transforming from one phase to another phase. So, during this transformation in the very initial period, normally nucleation normally happens. So, nucleation happens at the same time at the different positions and different grain boundaries. So, once nucleation over, then there is a growth stage actually starts. This growth stage starts, and of course, this is kind of typical S kind of curve, and of course, we can find out the rate of the growth in particular point. We just if you look into the fraction of the transformation, also fraction of transformation, this is the fraction 0. So, that means one phase to another initially is the very initial phase. So, then change of the phase. So, it is consumed the old phase creating this thing and following this curve, and finally completely transformed to the new phase. That means 100% transformation happens at this point, and of course, it starts from this point and it transformation ends at this point. So, we can say this is the more or less it is a total transformation time. So, that it transforms from one phase to another new phases. But of course, the nucleation happens with thing, but nucleation may also happen in between the growth stage also, that happens simultaneously, but rate of nucleation probably less during the growth stage. At the same time, maybe at the initial phase the growth stage is rate of the growth or is maybe less, but in the later stage the growth rate is more actually, and that is the typical nature of the transformation kinetics, and in case of it may be either solid state or in case of the solid to liquid phase transformation. Now, we can look into that phase transformation and recrystallization phenomena, which is relevant to the manufacturing processes, what we can link and how it is helps to explain the different phenomena in the perspective of the different manufacturing process. Actually, that recrystallization is mostly associated with the metal deformation process, and normally in general conventional metal forming process is associated with the metal deformation process. So, therefore, this may happens, metal deformation may happens in the cold process in the sense the nearly very low temperature the deformation phenomena may happen. So, in cold deformation process, definitely most of the cases it is associated with the metal forming processes, and of course, we can look into the rolling these manufacturing processes such as rolling, extrusion, forging, wire drawing. These are the associated with the cold deformation process, and this deformation normally happens at very low temperature. Therefore, this deformation at low temperature, but deformation may happens even at very high temperature also, and that can be called the hot deformation processes, or maybe hot forming processes we can say that that may happen at relatively higher temperature. Of course, this deformation process, or maybe we see exclusively in recrystallization process, that does not involve any kind of the change in the phase transformation happens, one old phase to new phase happens during this process, but not necessarily it will be associated with the change in the composition most of the cases. Therefore, cold deformation occurs normally this temperature range at 30 to 50% of the melting point temperature. Within that range actually cold deformation normally happens. So, but when the deformation happens in a metallic sample, the during deformation process, if we further apply the mechanical load from outside, so deformation happens, it creates lots of defects. That means defects in the sense, and the point defects, may be substitutional or interstitial point defects may also happens. Then dislocation density or the surface defects increases. So, that means during the material deformation process, the what way we analyze the imperfection in the crystal structure, that is represented in terms of the different kind of the defects. So, that means it may be point defects, the line defects, or maybe surface defects. So, that point defects, line defects and surface defects normally increases with the deformation of a during the deformation of a particular material. So, for example, point defects increases, and during the cold deformation process dislocation density also increases. That means there is a formation of a large number of dislocations if we further deform the material. At the same time, it may also associated with the surface defects may also increase during this deformation process. So, once there is a large number of deformation actually defects, crystal defects creates with the application of the load or during the deformation process, then each and every defect is normally associated with some amount of the strain energy, and that increasing number of the defects means the strain energy stored within the material, and that strain energy, the source of the strain energy is basically from the if you look into the balance of the energy, what external force we are using, that external force some part is converted to in terms of the internal in terms of the defects, and defects is stored create some amount of the internal strain energy of a particular material. So, then simple way we can say, if there is a deformation of the process, there is a storage of the strain energy in that case. So, now most of the cases if we see the practically, that once the after doing the material deformation process, we normally try to follow some kind of the heat treatment process. So, normally we follow the annealing processes such that the deformed grain can shape, or their existence of kind of internal stress exists after the deformation. That stress can be relieved if we do follow some kind of the heat treatment process. So, therefore, heating of the material of a metal means after performing the this kind of material deformation processes, for example, rolling, extrusion, forging, wire drawing, after that we try to follow some kind of the heat treatment process, normally annealing process. So, therefore, annealing process is followed in controlled way. So, we just simply heat the sample at the particular temperature and keep it for a sufficient time, and to try to follow some controlled cooling of this process. So, this is the typical features of the annealing process. So, now when you try to follow the annealing process in that in any kind of deformed product, in that cases that recovery, the phenomenon recovery normally happens at low temperature, or at high temperature normally the recrystallization actually happens. So, it can be explained in that way that during the annealing process, so the there is a increment of the dislocation density and there is increment of the point defects. So, therefore, when we try to recovery process, that means it is a annihilation of the some amount of the dislocation normally happens, and they actually reduce the strain energy, internal strain energy which was associated with the crystal defects. So, that actually reduces, but this process is called one recovery, and of course, recrystallization process occurs. Recrystallization means during the annealing process there is the strain energy accumulated in such a way that release of the strain energy normally happens by formation of the new small grains through the nucleation mechanism. So, once nucleation as well as the growth of this nucleus. So, in that mechanism, so that is simply called the recrystallization process. So, in general we can say the recrystallization means formation of the new grains by consuming the old grains when you try to follow the annealing process of a already hot work or cold work component. Now, of course, in this process if we follow this annealing process, there are high energy state to low energy states normally happens. So, from higher energy level to the lower energy level normally happens, and that is this energy level state with the application during the annealing process. So, if you do the further anneal, that means if you keep for a longer time follow the annealing process, then what happens? Then normally growth of the grains, already recrystallized grains normally grow, and if you keep the further annealing, if you keep alive the further annealing process. So, therefore, we can see that when you try to do the follow annealing process of a deformed material, then there is a follow the recovery. First step is the recovery, then recrystallization, then grain growth happens. So, that is why we normally say the recovery, recrystallization and grain growth phenomena which is associated with the metal forming processes. So, therefore, driving force in the free energy stored in the if we look into that, try to analyze the recovery process. So, the stored energy in the form of the point defects as well as the dislocations, and that associated with the recovery process. Now, if you look into the recrystallization, the stored energy driving energy actually comes from the only from the dislocation. And of course, if we look into the grain growth phenomena, actually the driving force for the grain growth phenomena is associated with the grain boundary. So, storage of the energy within the grain boundary. So, that is why recovery, recrystallization, grain growth, all phenomena, it is associated with some kind of the crystal defects. Maybe in case of recovery we just discussed point and dislocation. For recrystallization only the driving force, for recrystallization only the dislocation density, and of course, in grain growth only the grain boundaries. So, now recovery and recrystallization normally happens together during the metal forming process. So, it can be static recovery and recrystallization, but static recovery and recrystallization normally happens after the deformation process, and of course, this process is very slow process. So, sometimes we call the static recrystallization or and static recovery is a very slow process and normally associated with the after the deformation process happens, and of course, it is normally associated, maybe we can say, the cold deformation process. But dynamic recovery and dynamic recrystallization, it is also happen even during the deformation. The same time the dynamic recovery and recrystallization normally happens during this process. So, dynamic recovery recrystallization means even during the deformation there may be the some amount of the dislocation may be rearranged themselves such that it lowers the state of the energy, and of course, at the same time there formation of the new grains also through the nucleation mechanism. So, that but even that dynamic recrystallization and recovery normally happens even during the deformation process, and it is mostly associated with the hot deformation process. Now, in recovery, what a recovery happens? Recovery is mainly associated with the or accomplished recovery process is accomplished by reducing the point defects during the deformation, and of course, at the same time annihilation of the dislocations and their arrangements into the lower configuration. Annihilation of the dislocation means for example, the orientation of dislocation, one left hand screw dislocation, another is the right hand screw dislocation. So, they come into together in such a way they can neutralize their effect and lowers the state of the energy. So, such that if they rearrange themselves in such a way it lowers the energy. So, that process is normally called the recovery process during the recrystallization phenomena. But recrystallization normally happens that already discussed the recrystallization, there is a not rearrangement of the dislocation, rather the during the deformation process it creates a situation such that it overcome certain amount of the dislocation density, then nucleation starts at the particular point. The favorable position of the nucleus most of the cases is near about the grain boundary. So, where there is accumulation of the dislocation happens during the deformation process, and when this accumulation of dislocation density exceeds some critical limit, then at this point there may be formation of the nucleus and the nucleus further grow. So, this is normally called the recrystallization mechanism, but this recrystallization happens particular temperature. It can be defined that the recrystallization temperature in such a that 50% of the metals recrystallize in 1 hour, in which temperature, that temperature we can see the recrystallization temperature. But recrystallization temperature is not a fixed temperature, it normally happens over a range of the temperature, and particular material is a different composition and the stress, strain rate condition, temperature condition also it depends. So, therefore, typically 1/3 to 50% of the melting point temperature within that range we can say the recrystallization temperature, and in certain cases it can go to the 70% of the melting point temperature in a particular alloy system. But of course, I am not differentiating in details about the static recrystallization and dynamic recrystallization. The mechanism of static recrystallization and dynamic recrystallization are different. So, apart from the recrystallization also there may be some grain growth phenomena normally happens. So, there in these cases deformed polycrystalline material maintained at annealing temperature. So, definitely grain growth, the grain growth normally happens after the during the annealing process. So, annealing temperature and that and this normally happens following the first recrystallization forms, then that after recrystallization then grain growth normally happens, grain growth occurs. Now, driving forces of the grain growth is normally you can see that reduction of the grain boundary area and energy, and of course, the curvature of the grain boundary also influence the growth of the grain. Of course, big grains grow at the expense of the small grains. So, when there is a formation of the big grains, it just during the grain growth process, it consume the nearby or just attach small grains, and then once it consume the smaller grains, it takes a big shape. So, in that way big grains grow during this process, grain growth process. So, grain growth during annealing may occur in most of the cases or all the cases the polycrystalline materials, for polycrystalline materials the grain growth occurs during the annealing process. Otherwise, before annealing process, maybe initial stage of the annealing process is first associated with the recovery process, and then recrystallization process, and after recrystallization process the grain growth normally happens. So, therefore, it can be explained that boundary motion occurs by the short range diffusion of the atoms across the grain boundary, and of course, the strong temperature depends on the grain growth. So, grain growth normally it is strongly dependent on the temperature. Apart from the temperature, other parameters also influence during the grain growth phenomena. Now, if we look into that, what may be the modeling approach of the recrystallization, and when you try to explain the recrystallization, we try to look into that parameter that is called the dislocation density. So, that dislocation density is the parameter that is that can be linked with the mechanism of the recrystallization, recovery recrystallization, even for growth also. But what we can, if you know the dislocation, if we assume that dislocation density can be measured during the deformation process, but how this dislocation density can be linked with the recrystallization phenomena. Therefore, we can see that dislocation density actually evolves. If we look into that, if you deform simple sample, there is a generation of the dislocation there. So, further increase of the dislocation density. So, that but how dislocation density evolves, that dislocation density can be represented in that way. So, here rho is the basically dislocation density, and that delta rho by del epsilon is a strain. So, that deformation process we can characterize either strain or strain rate, and of course, at a particular temperature. So, we assume as a constant temperature. This is the strain K1, K2 are the constant, and this is the dislocation density. K1 and K2 are the strain hardening parameter, and as well as and K1 is the strain hardening parameter and K2 is the recovery parameter. So, strain hardening parameter is a constant in this equation, and with respect to that, and both K2 also constant, but K2 indicates the recovery during the recrystallization process. Of course, this is associated with the dynamic recrystallization. So, during the dynamic recrystallization, actually the nucleation and the strain hardening as well as the recovery, all this happens simultaneously, which is completely different from the static recrystallization mechanism. So, in this case, we can represent mathematically in terms of K1 and K2 the strain hardening effect and recovery term, and that recovery term we just simply multiply by the dislocation density. So, this is the normally we try to represent that how dislocation density evolves with respect to strain. Of course, we can easily convert in terms of the if we try to bring the time temperature phenomena, and we can introduce also that strain rate effect also. So, we can modify this equation to incorporate the effect of the strain rate. So, therefore, it is a general formula to represent the dislocation density as a function of strain or strain rate. that normally happens during the deformation process. But in a this dislocation density evolves, and what way it interact with respect to, or what way the grain growth normally happens if we consider all these phenomena, then we can develop some kind of the recrystallization model. It can be static recrystallization model or it can be dynamic recrystallization model. But only thing we need to know the equation for what way dislocation density evolves with respect to strain or strain rate. Therefore, we can from here we can estimate the recrystallized fraction, that means recrystallized fraction means the transformation curve, transformation from old grain to the new grain through the formation of the recrystallization. Now, that we can estimate the recrystallization fraction during the transformation process, and of course, it is possible to estimate the average grain size, that means in a average grain size of the recrystallized part on non-recrystallized part of a particular sample, that also you can estimate average grain size during this process. And of course, it is also possible to estimate the stress also during this recrystallization process. So, that is maybe associated with the some dislocation free yield stress value sigma 0, m is the Taylor factor, alpha is some constant, and mu is the shear modulus, b is the Burgers factor, and rho is the dislocation. So, once we from here we can estimate what is the dislocation density, and once we evaluate the dislocation density, from the dislocation density we can estimate what is the stress generate or variation of the stress during the deformation process, just by taking the information of the dislocation density evolves during this process. So, that is how we can estimate. Even apart from that, we already explained that average grain size can also be estimated. So, if we know the different mechanism which recrystallization mechanism is responsible, whether static or dynamic or other kind of the recrystallization, for geometric dynamic recrystallization or metadynamic recrystallization, if we know all these different types of the recrystallization mechanism, and we can develop the model, simple model, just by looking into the evolution of the dislocation density during this deformation process. Now, come to that next part of this module, that is the melting and solidification. So, melting and solidification, we can see that melting of a melting means we just, if we for a particular material or metal, if we apply the heat and at a particular temperature, there is a change of the transformation of the phase from solid phase to liquid phase, and then solid phase to liquid phase, when it reaches, then we can say this is a it is defined by melting point temperature of a particular material. So, once it is sample is above the melting point temperature with the application of the heat to that particular sample, then we can say melting happens. Similar way, if we try to allow cool of a molten material, so once it cross the below the melting point temperature, then we can say that it solidify. So, therefore, melting and solidification is normally associated with the several manufacturing processes, and here we try to look into the basics of the melting and solidification. So, actually before that we are always interested to know what is the melting of a pure metal and alloy. So, if we try to represent that some time temperature phenomena. So, this is temperature and this is the time axis. So, what happens if is suppose this is the melting point temperature, it represents the melting point temperature particular material. We assume the particular material means we assume the pure metal, such that pure metal having the single melting point temperature. So, suppose this is the melting point temperature line. Now, if we try to solidify this, so it comes from here. So, at this point, it is above the melting point temperature. So, we can say it is in superheated temperature particular material. When it come to this point, then it take the transition, keep sufficient time for a constant temperature, and then it comes to the gradually cool to the ambient temperature. So, this is the typical time temperature curve for a pure metal, but this zone we can say this is the transformation of the phase from liquid phase to solid phase. It happens over this time span. So, this time span we can say the solidification time. That solidification time, you just simply say that phase transformation happens within that period of time. Then further cool it comes to the ambient temperature. But why this finite time is required? Because in these cases there is a release of the latent heat of a particular material. So, during the release of the latent heat, the typical characteristic is that during the releasing of the latent heat, the sample remains for finite time at the same temperature. So, because it is a pure metal, so therefore, his melting point temperature is single point melting temperature. So, here this time the transformation normally happens from liquid phase to solid phase, that will we get some solidification time during this process. Now, if it is an alloy mixture of the different composition, so in that case the melting or solidification may not happen at a particular temperature, single fixed temperature, rather over a range of the temperature. So, such that within that range of the temperature, the Moussy zone, that means a mixing of the solid and liquid phase normally exists within that zone, and once it is a completely comes to solidify it, then it comes to the another temperature. For example, you can see this is the range of the temperature. So, it comes from here superheat temperature of this material. So, this is one temperature, this is normally called the liquidus temperature, this is normally called the solidus temperature. So, within that range it is not as a constant, rather it is there is a slope, phase transformation happens, then after that different slope is come back to this thing. So, here also this is the solidification time, but here the slope was parallel to the slope was constant, here it was the parallel to the time axis, but here there is some slope. That means change of the phase happens at the same time, change of that over a range temperature change. So, that this temperature range is called the solidus temperature and liquidus temperature. Now, if we look into over the range of the temperature in a particular single composition, so this is the so here we can see this is the, and this is we try to explain this as a particular alloy system. Now, say if we change the composition of the alloy system, then that solidus temperature and liquidus temperature can be different for a particular material. So, it may be something else in this case, such that here we can represent the solidus temperature and liquidus temperature for a particular composition. If we change now I try to explain this thing. Suppose this is the solidus liquidus temperature, this is the solidus temperature. If we project it here and say this is say x percentage A and remaining percentage of the B metal, B composition. So, in this case this is the liquidus temperature, this is the solidus temperature for a fixed composition. Now, if we change the composition, the liquidus and the solidus temperature can be different or must be different. So, in this case suppose other cases say here y percentage of A. So, then in this case this is the solidus and this is the liquidus temperature. So, in that way if we plot it and if we go at this point, we can say that here 100% A, that means it is a 100% A means it is a pure metal. If we try to mix A plus B and here say 100% B, it is also pure metal, and this is for pure metal. Suppose this is the melting point temperature, single point temperature. Here also 100%, this is the single point temperature. So, now if we change the composition of the A, decreasing A and increasing B such that A plus B always 100%, and then we can construct this kind of diagram. This is called the binary phase diagram. This is temperature and this is the composition. So, this type of diagram is very much useful, and when you try to analyze the solidification behavior or maybe solid state, even for solid state transformation associated with the alloy system. And of course, since we are using mixing the two components A and B, that is why it is called the binary phase diagram. So, this binary phase diagram with respect to the composition and temperature, we can get this kind of the diagram. Now, theoretically you can see the solidification time we define during the time of the release of the latent heat. So, latent heat means amount of the energy released or absorbed of a substance during a change of the phase. When there is a change of the phase, it may be liquid phase to solid phase or maybe from liquid phase to vapor phase. In that way also there may be associated with some amount of the latent heat. So, that phase change related to the phase change. So, in case of solidification, this latent heat actually released, and then during the melting of a material actually the latent heat is absorbed. So, how we can measure estimate what is the amount latent heat, that Q equal to m into L. What is the Q is the latent heat here, m is the mass and L is the specific latent heat, such that we can specific means per unit mass. So, this is the amount of the total latent heat we can estimate. Now, if we try to analyze what way the solidification front moves. So, for example, there is a solid phase, some interface, and there is a liquid phase. Now, have a particular situation, this is the some intermediate phase between the solid and the liquid phase. Now, heat flow during generated due to the phase transition. So, during phase transition we can say that total heat flow during the phase transition is this is the density rho, L is the latent heat, and V is the actually the interface migration rate. That velocity means we simply understand the what velocity the solidification front moves. So, during the solidification there is a formation of the solidification front, that is the boundary between the liquid and the solid phase, but how this front moves, that is the velocity is V here. So, here we can estimate the heat flow during this phase transition is that rho L into V. L is the latent heat here, because during the solidification the latent heat is actually released, and when there is a releasing of the latent heat, then what way the front moves. Therefore, solid liquid solidification rate means we understand the at what velocity solid liquid interface actually moves. So, suppose it is velocity v vector in the form of a vector here. Now, heat transfer in the solid phase. So, therefore, it is making the balance. The heat transfer in the solid phase we can estimate, we assume this the heat transfer in the solid phase in terms of the vector Qs. The Ks is the thermal conductivity of a at solid phase, and this indicates the gradient of a temperature. So, that means we know if we simply apply the Fourier's law of the convection we have already discussed, we can use the k into dt by dx is in one dimensional case. In 1D we can estimate q equal to minus k into dt by dx, but if 3 dimensional we can use this gradient term in the vector form, then minus ks delta Ts. So, delta Ts is nothing but is a temperature gradient here dt by dx, which equivalent to one dimension case. Now, minus Ks the gradient, this indicates the heat transfer during the solid phase, in solid phase during this process, solidification process. Now, similarly heat transfer in the liquid phase also we can estimate that minus Kl into delta the gradient of TL. So, that is the temperature gradient, and Kl is the temperature gradient with respect to the liquid phase in liquid phase, and Kl is the heat transfer thermal conductivity for the liquid phase. So, therefore, if we look into this all aspects, the heat flow generated during the phase transition, this is the heat flow generation of the heat flow. Now, if we try to make the energy balance or energy conservation during the solidification process, it is simple way that what is the heat generated. So, heat generated due to the phase transition, that means simply this heat generation due to the phase transformation bit what we are manipulating the latent heat during this transformation. Now, this is the heat generated term, then heat transfer in within the domain, and then what is the heat transferred out, and that clearly indicates the energy conservation during the solidification process. Now, if we put it that Qt basically energy generation, Qs to the input, and this heat transferred out in the this QL, such that heat transfer from the QL, that indicates that, making the equation like that Qt equal to this, and Qs if you go other side also it plus Ks delta Ts minus KL delta TL. So, if you have all this information, all these parameters, and this temperature gradient in the solid phase or temperature gradient in the liquid phase, we give you all this information, and we can do further calculation of the what way we can move the solidification front. But of course, during the solidification process, the what way the degree of undercooling actually exist, that degree of undercooling is the temperature difference below the equivalent temperature of the melting. That is most important to consider to explain the solidification behavior. But of course, this energy balance may exist in a particular zone, and then it is not necessary it is a balance overall, it is a very big domain, rather than it is a small very localized zone. If you look into this energy balance, it creates the very complex solidification solidified structure during the manufacturing process. So, therefore, because the solidification is mostly associated with the casting and the welding process in general. Now, this solidification in terms of the heat transfer analysis, it becomes more complicated if we look into the all phenomena, if we try to incorporate the kinetics of the solidification, then the behavior of the solidification or getting the simple equation is difficult, and if you look into the actual kinetics of the solidification. But of course, the kinetics of the solidification also important to explain the solidification behavior in manufacturing process, specifically in casting and the welding process. The actually solidification process is associated with the nucleation. What we explain the solid state phase transformation, there also nucleation was there, even for liquid solid to liquid phase to solid phase during solidification process, it is also associated with the nucleation process. But the nucleation may happen homogeneously, or nucleus may happen the heterogeneous, both the way, homogeneous nucleation, heterogeneous nucleation. And of course, in these cases what are the driving force for the nucleation is most important, because in case of the homogeneous nucleation process, the driving force may be the undercooling that exists, and this mostly associated with the pure metals. Now, in heterogeneous nucleation process, the driving force mainly the some kind of inoculating agent or some kind of the particle just actually introduce the nucleation process there, or maybe that interface, presence of the interface that actually helps for the heterogeneous nucleation process. So, anyway, we will try to discuss all this homogeneous heterogeneous nucleation process in details calculation in the respective module, but here try to give some overview of these things. And of course, most of the cases the important aspect is the microstructure after solidification, which is mostly driven by the solidification kinetics, rather than only we cannot predict the microstructure just simply looking into the heat transfer phenomena in a solidification process. So, therefore, it is very important to know the different nature of the nucleation process and what are the driving process, and how these driving forces normally is influenced by the different kind of the solidification process. For example, the driving process for casting and welding may be different, and different situation can be created, that means homogeneous or heterogeneous nucleation process in solidification, during the solidification, depending upon the nature or type of the manufacturing processes. Now, apart from that, there is additive manufacturing. So, in additive manufacturing is a nowadays it is a one attractive technology, and now it is a gradually more rapidly developing this additive manufacturing technology. But additive manufacturing, simply we understand that apart from the subtractive we follow in machining process, we can create any kind of the complex shape just by layer deposition of particular material. So, according to the American Society for Testing and Materials, the additive manufacturing is defined like that: process of joining materials to make objects from a 3D model data, usually layer by layer, as opposed to the subtractive manufacturing methodologies such as traditional machining process. So, it is completely opposite, different from the approach methodology we use in case of machining process. But of course, objects can be created from the 3D model. Suppose we want to create any model, any geometry, but we have to predefine that geometry, and that geometry is simply created the deposition process following the layer by layer. So, therefore, there is a loss of the material, what we generally observe in case of the machining process by just removing of the material. It is absent in case of additive manufacturing technologies, but there may be other difficulties, other complexity exist associated with the manufacturing technology or additive manufacturing technology. So, this additive manufacturing are synonyms to the 3D printing processes also, and sometimes we can say the 3D printing process. Of course, Apart from this additive manufacturing process, the allied processes that people works or already developed processes or more relevant, more close to the additive manufacturing process, that is called the injection molding. It can be powder based, metal based, ceramic based injection molding processes. And that also produce the complex and very high volume almost net shape components, what thing we can get from the additive manufacturing technologies also. Even power sintering process, which is more relevant associated, the concept is more relevant to the additive manufacturing technology. Apart from that, hybrid, that means additive and subtractive manufacturing also developed, and just one example of the laser cladding process with the traditional machining process. So, in these cases a laser cladding process we can produce the product, but unwanted things we just simply remove by following the traditional machining process. So, it is a approach, it is called the hybrid process, deposition also there, at the same time we are following the machining process. But in these cases we try to bring the machining process to get a good surface finish of a further product. So, that is the more relevant or more related to the additive manufacturing process, but of course additive manufacturing process or technology is completely different from all these three processes. In general, it is associated with the first material. So, material mostly used in the form of the powder or wire. Then what type of the system we are following, that means development of the technology in the additive manufacturing technology, whether directly we are using the wire or we can using the powder, or whether we are sintering the powder or whether we are melting the powder. That is the system is the next important part in additive manufacturing. Then software is required to create the CAD model, and maybe after creating CAD model means just geometry, you need to create the geometric features of a particular component, which component we try to produce by following the additive manufacturing technologies. Then design, application design, that means if we try to achieve layer by layer deposition, what strategy we need to follow, which layer should be deposited first and which may be deposited later on, and what may be the time gap between the deposition of the first layer to the second layer, because if it is assisted melting, some time is required to solidify the material. So, all this matter. So, that is called the designing of the process or maybe application. Just by looking into the application, we need to design the process. And finally, the production means once looking into all this aspect, we develop the machines or machines are available additive, then using these machines we can look into the what we can increase the rate of the production. So, all these 5 elements are associated with the additive manufacturing technologies. Now, in general, if we look what are the developed additive manufacturing processes, overall if you look into that, the application is either in the polymeric material, the two basic parts, either in the polymeric material or metallic material, or it is also possible to create some kind of the functionally graded material. So, that is combining the two different metal depending upon the applications. Now, apart from the application area process, the additive manufacturing process is developed based on the looking into the liquid binder and the curing process. So, this process is developed, it is a very old process actually in additive manufacturing. So, we use the liquid binder, we just fill the using the liquid binder, and then once we fill the liquid binder certain dimension, then or maybe layer of the liquid binder is existence, we just focus on the some laser or ultraviolet ray to cure only that particular part of this component. So, that particular part of this component once is cured, and if we follow this way, then we can create one kind of the object, that is the in principle the liquid binder and curing process. Then apart from that, melting and the solidification also, we just in additive manufacturing process we use the metallic powder, but in metallic powder if we focus the laser beam or electron beam, fuse it and melting, and then after that it is solidified. But the quality of the product or maybe surface accuracy depends on the particle size, and then of course all other, there are so many parameters to control to look to get at the good surface finished product. So, it is associated with the either solidification or melting, or in certain cases we follow the sintering process, and the sintering process means we just melt, not melt actually, we just put the temperature below the melting point temperature, and similar strategy we follow what you can do the powder metallurgy techniques. So, therefore, sintering can be another option. So, these are the three basic mechanism. Based on that, different additive manufacturing processes has been developed. But of course, materials is used in the form of either in the form of the powder or direct wire. We can use it, we can use the wire, and we simply heat the wire, and that wire has been deposited according to the desired shape. Of course, this deposition can be follow some predefined path, and of course, the additive manufacturing has also been developed using the sheet also. By stacking of the sheets, the techniques can be developed also. And of course, apart from this, directly using these things, there is a development of the conventional welding process converted to the additive manufacturing, or we can say the metal printing processes. So, the welding process is associated with the material deposition. For example, simple example, gas metal arc welding process. So, it is associated with the metal deposition process. So, what way we do the multi-pass welding processes. So, in deposition in the several layer, but of course, in a very controlled way, and that controlled way, and that can be used to develop the different type of the 3D metal printing process or additive manufacturing of metallic materials. Now, coupling of the different mechanism. Now, the last part of this component, we can look a little bit that if we look into manufacturing problems, we can see that for different manufacturing processes, if we analyze that, there is a need of the direct or indirect heat generation, either heat generation, or this heat generation can be done in the different way also. We can directly use the, in case of welding process, we can use directly arc, we create the arc, electric arc, but passage of the current is required, electric arc, or we use the electric current in such a way there may be some resistance. So, that resistance follows some Joule heating fundamentals such that heat generation may also happen at the interface. But at the same time, electromagnetic can also be created, and then electromagnetic, but in these cases electromagnetic create in such a way that it creates the high impact of the solid deformation process, what we have seen the electromagnetic forming processes. So, there also we can use the electromagnetic force, but at the same time electromagnetic analysis process can also be used to create the induction heating phenomena. So, induction heating, we just create the situation such that eddy current will be created, that eddy current will be responsible to generate the heat. So, that way also we can create the heat also. Apart from that, direct mechanical energy we can use in the solid state deformation process or manufacturing process. So, these are the different way we apply the direct or indirect way, different heat sources required to generate the heat, and then we can develop the different type of the manufacturing, different manufacturing technologies. But of course, when we analyze all these manufacturing processes in general, it is associated with the thermal process. So, that means temperature distribution, it is associated with thermal process, but once there is a heat generation, definitely some kind of temperature generation will be there, and that we use temperature analysis can be done some following the different thermal model. Then once it is thermal model, if there is a temperature difference between two consecutive points, it is maybe associated some kind of the thermal strain, or if there may be associated with some kind of the concentrated load or external load, that creates a kind of stress generation or deformation of a particular material, that is normally called the mechanical analysis. So, thermal analysis, mechanical analysis, but this mechanical analysis when or thermal analysis when it is associated, some kind of the microstructural transformation may also happen. That way we explain that there may be phase transformation, it may be that phase transformation that may associate some amount of the strain, but it is a very localized position, or if we look into very small scale, then we will be able to realize this kind of the transformation. So, that transformation is called the metallurgical transformation. So, the metallurgical transformation actually influence the stress generation or residual stress during the manufacturing processes. So, that actually thermal model influence the mechanical, and the mechanical model is influenced the metallurgy, is influenced by the mechanical model is more. But of course, this metallurgical transformation may be associated some kind of small, even it is in very small, some kind of the heat generation it may be associated with. So, but link is very weak between thermal and metallurgical model, but link is more strong between the metallurgical and mechanical model. So, that it is a some algorithm is required actually to coupling all this thermal, mechanical and metallurgical model. If you try to develop, it is a very good model which is associated with any kind of the manufacturing processes. But apart from that thermal model, if we take the even for fusion welding processes, it is also associated with some amount of the fluid flow. So, therefore, if there is a material flow, in that cases we need to develop the fluid flow model, and what the fluid flow model and thermal model, they are associated with that, because fluid flow model will give the velocity field actually. But if you look into that already discussed in the transport equation, energy conservation equation, the energy conservation equation, we can see that transport of the energy also important there. So, that transport of the energy is basically this velocity field actually influence the transport of the energy, and it is finally influence the temperature distribution. So, therefore, it is having strong relation between the thermal and the fluid flow model. And if we analyze the fluid flow model, then of course, we need some kind of the information which are temperature dependent, and when you try to look into temperature dependent properties also, then we need to know or should know do thermal analysis. So, therefore, or having some relation or some link in certain way between the different kind of the analysis procedure. But main important part is that when you try to, it is a complex model situation, then the important part is that what we are coupling all these phenomena. So, that is why this model is called as the coupling of the different mechanism. But of course, when you look into the different metallurgical transformation during this process, deformation process also, that associated with this create some kind of the micromechanics model, and then incorporation of the micromechanics model enhance the quality of the simulation process also. And once it is a kind of when it is application of the heat, and then thermal analysis, if we do thermal analysis also, then in cases during the solidification process, it is relevant to the thermal analysis or heat transfer analysis. But of course, if we understand the solidification process more clearly, if we try to develop the model of this process, the kinetics of the model is more important, and that kinetics is very much relevant to the metallurgical field which is related to the different types of the materials handling, or what we are applying the heat to the particular manufacturing process. So, then similarly in solid state deformation process also, and then mechanical deformation process, the recrystallization kinetics also important. So, when you try to do some mechanical analysis even for say metal forming processes, if we develop the some model, we need to know what are the recrystallization kinetics and what type of recrystallization mechanism actually prevails, such that this information, if we pass the mechanical model, it improves the quality of the simulation of a particular manufacturing process associated with the mechanical deformation. Of course, if we look into the transport phenomena, it is here also associated with the mass transport to the system, then it becomes more complicated. And of course, separately when you try to the fluid flow field, that the fluid flow field normally we get from the momentum equations. So, overall if you look all this phenomena, or if you know what we can coupling all this, but finally we need to look into that to represent all these phenomena, what are the governing equation we need to use. For example, if you look into thermal analysis, we need to go for the heat conduction equation to solution of the heat conduction, that is the governing equation of this process. Or of course, if you look into mechanical analysis, then we use the constitutive relation, for example, what way the stress is related to strain, and what we can relate between the deformation and the strain. So, that follows some linear or non-linear relationship, and that actually in plastic deformation it becomes definitely it is a non-linear relation between the stress and strain and all these cases. So, that creates kind of the constitutive relation, or constitutive relation can be developed if we know the between the two parameters. So, it is often used the constitutive relation when you try to develop the different kind of the model and in manufacturing process. So, thank you very much for your kind attention. I hope you are able to understand the overall idea of the physical mechanism associated with the manufacturing processes. So, next module we try to discuss about the different types of the manufacturing processes. Thank you very much.